All right, so what we're going to do is we're going to look at a variety of flammable compounds. Things like methane. Methane's highly flammable. What makes methane so electron rich? It's because of the carbon. What is the charge on carbon? 4. Plus 4? Well, hydrogen is plus 1. We can put it in parentheses. So we have 4 of those. That means carbon is 4 minus. In order for this to balance out, carbon must be 4 minus. So I'm going to put minus 4 in parentheses. You know, for a charge, you usually write the number and then the charge. But for oxidation states, we usually write the charge and then the number. So minus 4 is usually the way it's written as an oxidation state. But as a charge on an ion, we write it 4 minus. That's pretty electron rich. You know, what does a charge range for carbon, the oxidation state range? It ranges from, yeah, exactly, 4 minus to 4 plus, or minus 4 to plus 4. And so, at one end of the spectrum, we have methane, which is highly flammable. At the other end of the spectrum, we have CO2. Is CO2 highly flammable? No. Can you burn CO2? Not really, not with oxygen. And the reason you can't burn it is because, let's take a look. What is carbon here? Plus, well, oxygen is what? Yeah, oxygen is 2 minus. So we only have 1 carbon. That 1 carbon has to take care of all that charge, which is, yeah. And so it's plus 4 and minus 2. Now we can take electrons from oxygen, but is it easy to take electrons from oxygen? No, it's hard. It's like trying to burn water. You know, in water, oxygen's minus 2. Is water highly flammable? Not at all. You'd need some unusual oxidizer to burn water. Is it possible? Yeah, it's possible to burn water, but you would need an unusual oxidizer to do that. And so this is what we can call completely oxidized. So if we take our methane and burn it all the way to CO2, then it's completely oxidized, but we might not, you know, because we might partially oxidize it. If we partially oxidize it, it could oxidize to, rather than carbon dioxide, we might actually form carbon monoxide. Does carbon monoxide, is it flammable? Yes, carbon monoxide is flammable. Why? Because it doesn't have a lot, but here it is, carbon's plus 2, but it could lose an additional 2 electrons. So an oxidizer can come along and take 2 more electrons from carbon. How about soot? Soot is carbon in the 0. Yeah, soot, each carbon atom in soot is capable of losing 4 electrons. But methane is the best because methane is capable of losing how many electrons? In going from minus 4 to plus 4, how many electrons were lost? 8 electrons. And so we lose 8 electrons here. So this is the richest. This can lose 8 electrons. This can lose 4 electrons. This can lose 2 electrons when we combust it. Okay, that's methane. But what about ethanol? Let's take a look at ethanol. So if we have ethanol, which is a formula for ethanol, the way I'm going to write it is, I'm going to write it, you know, ethanol is typically written CH3, CH2OH. But what I'm going to do is for oxidation states, it's probably easiest to combine everything. So altogether I have 2 carbons, altogether I have 6 hydrogens, and 1 oxygen. So I'm going to write it like this, C2H6O. Oftentimes, ethanol is written C2H5OH, you know, because the alcohol part OH. But either of these 2 work for figuring out oxidation states. This one might be easier, but we should be able to do this one. Hydrogen is what? Plus 1. Oxygen is minus 2, which makes carbon what? So we'll do it here. Oxygen's at -2, hydrogen is a +1. We do hydrogen first. Hydrogen is +1, oxygen is -2, and that leaves carbon at. So this -2, this is going to be +6. -2 + 6 would be +4. That means altogether this has to be a -4, which means each carbon is a -2. So if it's a -2, it's capable of losing 6 electrons, right? Not the 8 electrons like in methane, but 6 electrons is pretty electron rich. You see that? Now, if it were to lose all 6 electrons, it would go to CO2. But that doesn't always happen. It depends on how strong of an oxidizer you react with. If you react with a powerful oxidizer, it takes it all the way to CO2. But what if you have kind of a weak oxidizer? If you have kind of a weak oxidizer, it doesn't. So for example, in wine, did I talk about this? You know, I didn't do that. Many years ago, I went camping in Joshua Tree. In Joshua Tree, there's some towns nearby. One town, Yucca Valley, they had a dollar store, 99-cent store there or something. Was it Dollar Tree? I can't remember. Big lots. I think it was big lots. So I went in there, and they had like wine, Santa Barbara wine, $1 bottle. Santa Barbara, because being from Santa Barbara, had to buy it. So I bought the wine, took it back to the camp site, and then tasted it. And you know what it tasted like? It tasted like vinegar. It was bad. It tasted like vinegar. You know what happened? What happened was a little bit of air got in there. You know, a little bit of air got in there, so a little bit of oxidizer got in there. You know, it wasn't like, it would have been okay if a lot of oxidizer got in there, because if a lot of oxidizer got in there, then it might have tasted like sparkling grape juice, because if a lot of air got in there, I could have oxidized all the ethanol to CO2 and I'd have sparkling wine. But it was only partially oxidized, and it partially oxidized it to CH3COOH. CH3COOH is also called, well, maybe if I wrote it like this, HC2H3O2, you call that acetic acid. And so what had happened was a little bit of air got in there, and it didn't oxidize it completely. It oxidized it partially to this. Actually, it could have been even nastier than that, because you know, normally what happens to alcohols in the partial oxidation scheme is they get oxidized in this sequence. This is what happened to my wine. The wine went from ethanol to vinegar, acetic acid, which is vinegar, by partial oxidation. This is partial oxidation. Or, you know, it could have been worse than that, because normally this is what happens with alcohols. With alcohols like CH3, CH2OH, they first get oxidized to this, CH3CHO. This one is called an aldehyde. This one's called acetaldehyde. Acetaldehyde is poisonous. It can be bad headaches and stuff like that. And so ethanol can be partially oxidized to acetaldehyde. Acetaldehyde can be further oxidized to acetic acid, 3COOH. Eventually, what we want in the body is we want the ethanol to be oxidized all the way to what? Complete oxidation. So if you consume ethanol, what's going to happen to the ethanol? Eventually you're going to, let's say, you don't excrete the ethanol. Your body's going to metabolize the ethanol. Ethanol has calories, a lot of calories, and the ethanol is going to be converted into what at the end? Well, all that ethanol, hopefully it doesn't, if you have too much ethanol, then you're going to go, like, think acetaldehyde, hangover, etc. But eventually, once you digest or process all the ethanol should be converted into CO2. And eventually, you'll just exhale it, after extracting all the energy you can from the ethanol. So that's complete oxidation. So what we have here is we have partial oxidation. These are the partial oxidation products, and then complete oxidation. And so this is what happened to the wine. I just had partial oxidation of the wine versus complete oxidation. And so what we can do is we can do this. We can figure out these reactions based on this. This is the whole thing about skeleton redox. In skeleton redox, the major products are given. The major products are given. So you saw the explosion for methane. I had the only explosion that I had in lab was when a student poured ethanol into a waste container. So the student, there's a waste container here, and the student was doing a makeup lab. And this waste container contained potassium permanganate and HCl. KMNO4 and HCl. It's a waste container. And so the student there were 2 waste jugs I set up because since they're doing makeup, the week before, this was in Chem 1B, the week before they were using ethanol. So I told the student, make sure not to mix the ethanol with today's waste. Today's waste contained, powerful oxidizers, manganate, HCl. And so there's one more waste jug set up, which was last week's waste. Last week's waste contained ethanol and other stuff. This other stuff. And normally when we set up waste jugs, we set up a waste jug for these, which we call oxidizers, reducers. Oxidizers. So it's okay if you have oxidizers poured into the oxidizer waste, because oxidizers versus oxidizers, they both want the same thing, so it's not going to react, right? So you can mix oxidizers together. You usually don't have any problems mixing oxidizers together. It's when you mix the oxidizer with the reducer that you get the problem. And so so I set up a waste, oxidizer waste, reducer waste. You know what the student did? They poured the ethanol into the oxidizer waste, and these are strong oxidizers. Ethanol is a strong reducer, and it exploded. And so this is why I spent so much time on redox, because I had that explosion in lab. But fortunately, this is a glass jug. It was one of those glass jugs that you see in the lab over there. But fortunately, it didn't blow up. It just, this huge explosion, and the flames shot up out of this. But the student was a little shorter, and so they had their head partially inside the hood as they were pouring the waste in, and so their face was first-degree burns all over their, and so got very, very lucky. That was it, and the hair was singed on the front. But it was a big explosion. Big explosion. But when you see all the explosions with methane, this is everybody has, people get relaxed, but methane's actually a pretty dangerous chemical. I mean, how many people died every year from methane explosions? And the same thing with ethanol. Ethanol, people drink this stuff, so you don't really think about explosions and this kind of stuff. But ethanol is a pretty good reducer because it's electron rich. I mean, carbon's in the -2. -2 is pretty good. And so that was the explosion. Now, what had happened? Well, this is a case where ethanol is not on the redox chart, but we know that a lot of flammables, are organic chemicals, and organic chemicals are carbon-based chemicals, and these carbon-based chemicals, we have lots. Like, for example, have you heard of bakeries exploding? Bakeries can explode because of powdered sugar and flour. Both powdered sugar is flammable, flour is flammable. Grain silo explosions that happen in the Midwest. Let's see, bakery explosions. When was the last bakery explosion? I track these too.
You might be surprised about how many people have been killed in bakery explosions. Oh, this is a gas leak in a bakery. Let's see. Images of bakery explosions. Although I think these are natural gas, but some of these are based on flour and sugar aerosols. And if you get it in the right mixture, it can be quite explosive. Actually, let's take a quick look. So all these grain style. I mean, grain's not as electron rich as sugar or ethanol, but that's a pretty big explosion there. There are lots of explosions here, and lots of people will get killed.
What is it in grain that explodes?
Yeah, the flour. The flour is flammable, right?
Wouldn't they put something down?
I guess 36 people died in this one here. 36 people died. It's dust, you can burn flour and it burns slowly, but when it becomes a fine dust that fills up the room, then you have potential for explosion, because then reactions can happen. It's like iron. Iron metal is hard to ignite, but iron powder, iron dust is easy to ignite. You can see that in sparklers, where they put iron filings, sparklers, and other stuff. So, watch out. So anyway, we can look like sugar. You know what is flour made of? Grain. Some of the bakery explosions, some of the, let's see, composition of flour. Chemical composition of flour. Maybe I don't want to spend too much time with it. Oh, no wonder I'm on YouTube. Well, anyway, things like sugar. If we look at glucose, C6H12O6, this is glucose, but this is not table sugar. Do you know what table sugar is? Table sugar is called sucrose. And sucrose is actually a combination of a glucose molecule and a fructose molecule that have bonded together. And so sucrose is C12H22O11. And so let's take a look at the oxidation states. What makes sucrose flammable? Like in the powdered sugar factory or confectionery explosion. So oxygen is going to be at -2. Well, hydrogen goes first. Hydrogen is always first at +1, and then oxygen is a -2 in these organics. That means carbon's at what? Carbon's at 0. Well, if it's at 0, you think, is that really electron rich? It is. It's capable of losing how many electrons? 4 electrons. That's still pretty reasonable. So sugar is also potentially explosive, as grain is, as this other stuff is. And so what's happening there? Well, this is what we can figure out. We can use skeleton redox to figure it out. It doesn't matter if it's sucrose, glucose, ethanol, methane. We can always figure out what the half reaction is. And so the skeleton method is to determine what the half reaction is. And so let's go back to the ethanol. If I go back to ethanol, it's CH3CH2OH. This is ethanol. And in that explosion, what do you think ethanol, do you think I completely oxidize it or partially oxidize it? in that explosion, do you think I converted the ethanol to vinegar, or do you think I went all the way to CO2? All the way to CO2. And so what's happening here is the ethanol eventually is going to end up in CO2. It's going to be completely oxidized in an explosion like that. And so if ethanol is converted into CO2, this is what we call a skeleton half reaction. The skeleton half reaction tells me the major product. The major product of ethanol is going to be carbon dioxide. Okay, then the skeleton half reaction does this. We balance things in a certain sequence. In step one, we balance all elements other than hydrogen and oxygen. By changing the coefficients. So the way I'm going to do this is, over here, how many carbon atoms do I have? On the left, I have 2 carbon atoms, so I'm going to write it in the box here. Well, on the right, I have 1 carbon atom, so what I need to do is I need to change the coefficient to 2. Then it's balanced. In the next step here, we're going to balance the oxygens by adding H2Os. So on the left here, I have 1 oxygen. On the right here, I have 4 oxygens. And so I need 3 more oxygens here. Therefore, what I'm going to do here is I'm just going to add 3 oxygens to this. So we'll go plus 3, not oxygens, plus 3 waters. Plus 3 waters. In the next step, we're going to balance the H's. Balance H by adding H plus. All right, so on the left here, I have 6 H's from ethanol plus 6 H's from water, so that gives me a total of 12 H's. On the right, there's no H's here, so I have 0 H's here. And so what I need to do is I need to add 12 H plus to balance it. So now I have 12 hydrogens on the left and 12 hydrogen atoms on the right. The charges aren't balanced, but we don't care about the charge yet. Not until this step. This is the step here that we care about the charge. Balance the charge by adding electrons, E minuses. And so what I'll do is I'll look. Ethanol has 0 charge, water has 0 charge, so there's no charge on the left, so I'll just write 0. On the right here, CO2 is neutral, but H plus is positive, so I'm going to have plus 12 charge on the right. So if I have a plus 12 charge here, I need 12 electrons because each electron's minus charge. And so the way I balance it is kind of strange because I eliminate positive charges. How many positive charges do I need to eliminate to get these to match? 12 of them, so I'm going to add 12 electrons to do that. And then I'm going to add these 2 up. When I add these 2 up, then I'll have the half reaction. CH3CH2OH plus 3H2O liquid yields 2 CO2s, gas plus 12H plus 12 electrons. We can check if this is balanced by checking the atoms. 2 carbons here, 2 carbons here. 1 plus 3 is 4 oxygens here, 4 oxygens here. And then 6 hydrogens here, 6 hydrogens, 12 hydrogens, 12 hydrogens. So the atoms are balanced. And then we check the charge. Ethanol is neutral, water is neutral, CO2 is neutral. We have 12 positive charges from 12 H pluses plus 12 negative charges. And so we got total charge on the left, 0. Total charge on the right is 0. And so this is what we call the balanced half reaction. Balanced half reaction. Now in this balanced half reaction, I can find out what happened in my explosion here.
that happened in lab. And so the explosion happened based on having potassium ions. So we're going back to the reaction here. Permanganate ions, H plus ions, chloride ions, water, and ethanol, CH3CH2OH. Now, we go through and we make the assignments here. The assignment would be potassium ions, off the chart, oxidizer. Permanganate with H plus, oxidizer. H plus alone, oxidizer. Chloride, reducer. Water, oxidizer and reducer. Ethanol, we said, is electron rich or electron poor. Ethanol is electron rich. Now, electron rich species are subject to oxidation. They're flammable. Good ones are. Which one's easier to burn? Chloride, like sodium chloride, water, or ethanol? Ethanol's not on the chart, but if you think about this, which one is easiest to burn? Ethanol. Ethanol. If you try to make a fire using sodium chloride, yeah, potentially, but no. Or water? No, but ethanol, yeah. And so even though ethanol is not on the chart, we can kind of mentally place it as a strong reducer. It's easy to burn. It's flammable. And then what's the most powerful oxidizer? The most powerful oxidizer turns out to be permanganate and H plus. And so here's our reaction. But in order to complete this reaction, we need the half reactions. Well, the half reactions, we have one here. One of the half reactions is the permanganate. So we can just write that down here. Permanganate's the fifth strongest oxidizer on the chart. So it's permanganate plus 8 H plus 5 electrons yields manganese 2 plus 4 H2O liquid. Now, what's a half reaction for ethanol? The half reaction for ethanol is here, and we did this assuming the ethanol is going to be completely oxidized to CO2. It should be. The ethanol should be oxidized to CO2. So we're going to add that here. This is going to be CH3, CH2OH plus 3 waters. This is going to yield 2 CO2s plus 12H plus 12 electrons. Do the electrons balance? No. Here I need 5 electrons. Here I'm producing 12 electrons. So how can I get them to balance? I need to multiply. So what should I multiply the top one by? 3. If I do 3, that gives me 15, but it still doesn't match. I gotta rethink. I need to multiply by 12. I'm going to have to multiply the top one by 12 and the bottom one by 5. And so that's going to go 12 permanganates. What's 12 times 8? 80. That's going to be 96 H pluses. 12 times 5? 60. It's going to be 12 Mn2 plus. 12 times 4? 48. And then the bottom one I'm going to multiply by 5. So that's going to give me 5 ethanol. 5 times 3 is 15. 5 times 2 is 10. 5 times 12 is 60. 5 times 12 is 60. So now I got it. I have 60 electrons here and 60 electrons here. They're going to cancel out like that. That's what we need. We can't have electrons left over because we can't bottle them and we can't buy them as bottles of electrons to mix these reagents. Now what we do is we'll just add them up. So I'll add up everything on the left. 12 permanganates plus 96H plus 5 ethanol plus 15 waters Okay, then I'm gonna add up everything on the right. 12 manganese 2 plus 48 water, plus 10 CO2, plus 60 H plus. Then I'm gonna look for driving force. So if I look for driving force, it's gonna be like this. Permanganate and H plus, that's our oxidizer. Therefore, manganese and water, manganese 2 and water should be our conjugate reducer. Ethanol and water here, this is going to be our reducer. And therefore, CO2 and H plus, this will be our oxidizer. So permanganate and H plus, this is our oxidizer. This is our reducer. Manganese and water, this is going to be our reducer. CO2 and H plus, this will be our oxidizer. And so what do you think is a stronger oxidizer? These aren't on the chart, but what do you think is a stronger oxidizer? Permanganate in acid or CO2 in acid? Permanganate. And so we don't even need the chart. This should be obvious. CO2 isn't that powerful of an oxidizer, is it? No, it's not like chlorine gas. Permanganate's even more powerful than chlorine gas. The chlorine gas is down here, permanganate's up here. Chlorine gas, you'll definitely know this, but we exhale this stuff, the CO2, and it's no big deal. And so that's stronger. That means ethanol is easier to burn than manganese 2 ions. Is ethanol easier to burn than manganese 2? Yeah. So that's going to be stronger to weaker here. So we have driving force. This was the explosion. And so, are we out of time? Oh, we're out of time. Shoot. Okay.